So basic thing. Before we start with the proof, let's see some basic of the that we need. All right. So some of the basic thing is that this is the one. Comparison. Okay, suppose functions. Okay. This is in X inside the A and B. X is between A and B. Okay. So how we picture that one. Okay. And we have there, and we have also so A and B is here. So the green one is G, and the red one is F. Okay. So what we see is that the integral, because the integral is area, see, so area under G is larger than area under F. It's integral. Positiveness first. Okay, so that's less than A of G. Okay, so this is what you call the comparison principle. So if F less than G, then it's positive. Then the integral is also less than that. Okay, so that's comparison. And this is based on all right, so suppose you have something like this. F is between M and M. X constant. So M is the lower bound, M is the upper bound. So lower bound. Okay. So using comparison principle, what we get here is that is less than this M and bigger than M. Okay, so what is this one? Well, this is the just rectangle. So I'll picture this. And we have, say, this one. And we have, this is M. And this one is, okay, this M. The green one is M. So area under a curve. Okay, this must be less than that. All right, so this equals to M times B minus A. This equals B. Okay. So that's the Comparison principle. That's what we need. All right, so let's proof of proof of this one. Okay, so let's so let fx equals to ftdt. Okay, and what we need to compute here is ddx of fa. Okay, so by definition, it is the limit. Okay, recall this is f of x plus h minus f of x over h. Okay, so we're computing this one. Let's compute this first without the limit. So let's simplify this one. Over h. And that is 1 over h, f of x plus h. So we a to x plus h have t dt minus from a to x. All right. Okay. And because we have additive, so here we have integral from a to equals to integral from a to x, right? Plus integral x, right? So if you subtract this one, so you get, this is what's left. Okay, so you have this one, x from, okay, by the additive of the of the of the intervals. Okay, so let's compute this one here. What is this actually? Now, since f is continuous, it is bounded, so um, it has say maximum and minimum, upper and lower bound. Okay. F is continuous on these intervals. It has upper, lower bounds. Okay, so we let m less than f of x less than m x between a and b. Okay, so to this one, let's integrate from x to x plus h. Okay. Great. So x plus h m. Well, sorry, f of t dt. Okay, integrate, and then this is m. Okay. And but this one is easy because this is constant functions. So it's just a difference. So this is just m h. This is just little m times h. the length of the interval. The length of the interval just h. Okay. So next is you divide everything by h. Okay. So what we have is that here we have 1 over h t. Okay. Divided by h, this is less than m. This one is less than so. All right. Okay. So m and m is the say the max or min or upper lower bound of f on say on AB on interval x. So we take now with m. Let's see the minimum of f t between a and so t between x plus h. M is the max. And now let's take the limit. Okay. As f is continuous, let's here f. Okay, so if you move this here, it goes to 0, right? The max and min, this is max, this is min. Okay, so it gets closer. Max, min gets closer. So m minus m goes to 0. Okay. All right, so the next is take limit. Yes, h goes to 0. Okay. What is this m goes to? This m goes to the value f and x. Well, that's this. Okay. So this take limit and using squeeze, right? 1 over h. H f t dt. This limit. So this gives you just f of x. Yeah, f of x. Right? So this is this limit. Equals f of x, right? So what is this? Well, this is the thing that we computed earlier. There. So this limit. So that is equals to ddt of a to x f CVT. Okay, so that's the fundamental theorem of calculus. Okay. Questions so far? Let's do some examples.
Sir, can you upward the screen a bit? Yeah, that one. Then, sir, thank you.
Okay, so let's do some examples. Let's pick up some problems. All right, so let's do some. So let's skip this one. Let's do two. T of x. All right, so examples. Let's pick some problems here. Okay. Oh, examples. Okay, so 17. The question is compute G prime. Okay, so the derivative. Okay, so G prime of x is the dx of there 1 to x to GDT. Okay, so what this tells you is that by FTC, 61 hour. Let's see. To t is continuous. Okay. Let's see. This is continuous. Okay, so it's okay to use this one because it's polynomial. From 1 to x, this is constant. And the upper bound is just x, the variable. Okay. So when you apply FTC, apply the fundamental theorem of calculus, the first one, the derivative cancel the integrals in this form. Okay. So cancel the integral, what you left is just not 2t, but 2x. Okay. This one, say that different derivative cancels the integral. Okay. So that's right. 18. Let's see. What that one? G prime is ddx of, so same as the above, except that um, the upper and lower bounds interchange, switch. So let's switch the integral first. Okay, but when you switch integral, then you have that negative thing, right? Negative, that's, yeah. So you have negative 2x. Okay, okay, questions? Let's do 20. The prime is the x of that. I won't rewrite the problems, but you notice that this one is continuous because on, let's see, this domain here between negative pi over 2 to pi over 2, cosine is continuous. Cosine 2t is continuous. You cube the continuous function, it's remain continuous. Multiply by tangent, which is continuous. So it is continuous functions. Okay. And here, that's a constant, and x is the upper bound, is the variable. Okay? So what FTC says that FTC1 says that well, the derivative cancel the integral. So what happened is just you get the f back uh, with x as variable. So it just replace t by x. Okay, so let's do 22. Okay, let's do this first. You don't need this one. All right. In computing indefinite integral, you see that uh, this t is, x is constant uh, with respect to t. Okay. With respect to t. Okay, because it's constant with respect to t and the integral is with respect to t, you can take this out. Yeah. Okay. So then what you compute here is now um, t prime is ddx of, let's say you rewrite this one, 1x xt dt, right? So that's equals to, you take the x out. Yeah. Okay. But here you have this times this. So this f, this is x, g of x. Okay, so product rule in this case. So the product rule is FTC. Okay, derivative of this, derivative of x, just one. So you get this one. Okay. Plus x times derivative of this. So this one gives you, let me just rewrite this. Because without FTC2, then you won't, we haven't computed this one. Okay. And right, so let's compute this one. X times this integral cancel the, sorry, in derivative cancel the integral. So just leave it just this one. It's just x. And without FTC2, so let's do this one. FTC2. Without FTC2, well, that's sort of quite complicated because remember you have two partitions. Let's say how to do this. We'll do that later. We'll compute this after FTC2. Okay, so just this one. So in a moment, just say this one. Just x squared. Okay. Right. Okay. What else? All right. So let's do 23. Fine. X 1 to x squared. So is it 1 to x squared? Yes. Sine t dt. The problem with this one is that um, while this one is continuous, no problem. This is constant. The lower bound is constant. This one is not really x, but x squared. So this is a functions. Upper bound is it's not variable, it's functions. So let's say let's do this one here first. Let x be negative from 1 to x, negative, sine t be t. Okay. So the thing is, what is this one? F of what? So what is the inside? What should be the inside?
Is it x squared?
Replace this. Okay, so that means this one is a composite functions. Composite functions. So in order to take derivative, you need chain rule. Okay, so this becomes, sorry, equals ddx fx squared. Right, so chain rule now. Okay, so it's chain rule. You get derivative of f x squared times derivative of x squared, which is 2x. Okay. All right. Now from here, FTC1, okay, f prime of x is just okay, t sine x. Okay. So now we can continue with f of f prime of x squared. So this sine x. Right? So replace x by x squared. X. Right, so let you do the other things. Okay, let's pick up some more problems. Let's examples. Okay, just a remark on the 26. Okay, so you see, uh, t to the fifth is a continuous. Doesn't mean because it's polynomial. The problem is the lower and upper bound. Okay, because the lower bound is now a functions and upper bound is also a functions. But first, what we do here in this case would be just a scratch this a little bit here. You split this becomes cosine x to a. What is a? It doesn't matter what a is because it doesn't count anyway. A to sine x. There, so like that. Then you have the first one. The problem is that the constant is in the upper bound, so we need constant in the lower bound. So switch upper and lower bound. When you switch upper and lower bound, you get negative. Okay, you switch this one, and you compute this one, the second integral. Let's use the fundamental theorem calculus one. Right, so that's the idea. Okay. Uh, okay, problem 27 to 32. Find intervals on which the graph is increasing in concave up. Okay, so just I just wanted to. Uh, I'll just do the 27. More uh, might be good. Just the 8. Um, 28. 28a. What we need is to find increasing. Okay, increasing. So what we need here is just to find this is. Okay, so what we need to compute is the derivative. Okay, let's compute that derivative. So we need sign chart. Okay, the prime is the derivative of square root of 1 plus s squared. So well, by FTC, let's see, this is continuous functions, all right? So continuous. The lower bound is constant, and the upper bound is variable x. So FTC holds in this case, and the derivative cancel the integral. So what we have is just replacing s by x by the variable. Right? Okay, so then let's do sign chart for f prime. Okay. So this holds for any x actually, because this is 1 plus x squared. So this is always bigger than 1, at least 1. So the square root is always positive, so it's never negative. So let's okay. So the only change of sign is when x. That's x equals 0. So that's so when x is positive to the right of 0, this is also positive. Okay, and x is negative, that is negative. Okay, so increasing. Here's the increasing part. So f is increasing on 0 to infinity. Okay, and concave up. Concave up is the second derivative. Well, that second derivative, that's easy, because you take the derivative of this one. All right. So you can write this down as just x times negative 1. So derivative of this is 1 times this. Times x times derivative of this one. So it become x plus x squared. Reduce the power by 1. Multiply by derivative of x squared, which is 2x. Okay, so that's x squared. So we write this down. No, that's don't need to. Just we need the sign chart. So this is just x becomes x squared. Okay, and you do factorizations. Okay, let's factor 1 plus x squared with the lowest degree, so it's -3/2. Okay, so this one is you just another 1 plus x squared. Okay. And this one minus x squared. All right, so just this one over 3/2. All right, and the sign chart would be, well, this always positive. Okay. It's always concave, concave, up. Okay. Okay. On, let's see. Yeah. Okay. Oh, it's 54 already. All right. Any questions? We should stop here.